Our next speaker is Nathalie, and is she there?
Yes, I'm there. Can you hear me?
Oh, okay. Bonjour, ça va?
Hello.
Oh, c'est parler français. Quelquefois, j'ai oublié tout mes français.
Oui, tout à fait.
Maintenant, on parle anglais. Maintenant, okay? Okay, so we have Nathalie, and she's an associate professor from the Sorbonne University in France, interested in partial differential equations, stochastic partial differential equations, kinetic theory, scaling limits, opinion dynamics, which I believe that you're going to be talking about, dynamics, graph limits, asymptotic preserving schemes, and also I see that you do is it like a podcast or like a blog called, you're going to do you have to do the translation. We go. How long will go? I say, is it a tete-a-tete, yeah?
Yeah, it's a bit difficult to translate because it's a play word actually. Tête-à-tête is when you're just speaking both of you, and in French the expression tête chercheuse is for someone who is a bit smart. He's smart, so tête-à-tête chercheuse is a bit of a play word.
Oh, okay, so having a head-to-head intelligent conversation.
Yeah.
Yeah, there you go. There you go. And my French is terrible, so I do apologize. But anyway,
no, not so bad.
Oh, thank you very much indeed. We're still voting for Brexit. Anyway, so where we go. Cool. All right, the floor is yours.
Okay, thank you. So I will start, try to share my screen. Let me know if you can see it.
Yeah, all good, yeah?
Okay, perfect. So first of all, a couple of things. Thank you very much for the two previous talks. That was very interesting, very nice. And I apologize, I had to miss the first one. I just did the two first one yesterday, and that was very nice too. And I'm looking forward to see the replay of the one that I missed, that I'm sure was amazing. I am so sorry not being able to be there with you. I would have loved to, but for calendar reason, I was not able to, but I'm very humbled to be part of such a nice event. And so thank you again for the invitation. So I was planning on doing the following. I will start by telling you a little more, a little bit about my mathematical interest of the past few years. And then I will finish by saying a few words about my mathematical journey, as I've been kindly invited to. So we'll start discussing about some topics about collective opinions, social dynamics. So let me set the framework, the introduction. So I'm interested into what is called social dynamic models. So those are the system of ODs, as you can see here. So basically, you are dealing with a population of n agents. And so let's say that here, this represents the opinion of agent I. So typically imagine, for instance, that xi is a quantity which lives between 0 and 1. And for instance, if it is your political opinion, let's say on 0 you are far left, and on 1 you are far right. And so you can put an opinion somewhere here to represent your position. And so typically the model is the following, is to say that when you discuss with other agents, so for instance here, this is agent I discussing with agent J, this can make your opinion change. And so the thing is, you have here a quantity which is important, which is called an interaction coefficient, and which is here to represent the fact that actually on life, not everyone has the same impact on you. If you discuss with your parents, your wife, your husband, your children, it will not have the same effect as if you discuss, for instance, with your neighbor that you see only twice a year. So this is encoded into that coefficient, which is here to model the impact of agent J on agent I when they exchange. So a typical example is what is called the Exelman-Krauss dynamics, where typically your interaction coefficient is taken as following. So you have a function which only depends on the distance between your opinion. This is also to model something that maybe you've observed. It's the fact that sometimes when you discuss with people, if they have opinions which really are too far away from yours. Let's say, for instance, if you sit at two opposite sides of the political spectrum, there are actually few chances that they manage to make you change your mind. So typically here we work with compactly supported function, meaning that when your opinions are too far away, well, the person actually has zero impact on you to make you change your mind. So when you are interested into this model, there are plenty of questions you can ask yourself. The first one is, what is the long time behavior? So typically in the picture that you can see here, here is the time. Here are the different opinions of the population, one color by agent. And you can see that actually when time evolves, at the end, you reach consensus, meaning that the population only have one opinion. Another phenomenon that can be observed for this model is the cluster, meaning that at the end of the day, you have a finite number of opinions. So this is actually reminiscent of maybe a phenomenon that you have that you already heard of, which are echo chambers into social media, where you see community which polarized and at the end finish with very different opinions. So those are the things that can be modeled with this approach. So this is the first type of question you can ask yourself. And actually, I've been working on the second type of question, which are the large population limits. So typically, I told you n is the number of agents. So the question is, what happens when n goes to infinity? So there is actually a lot of possible approaches for that. The classical one is from, it's called the mean field limit. So this is an approach which actually comes from physical gas dynamics, but that can be extended to a social dynamics model. So when you're interested into what is called mean field limits, the thing is, it's as if you were de-zooming, meaning that you're no longer interested into following each agent, knowing at each time what is the opinion of each agent, but you're more interested into the big picture. So typically you change your quantity of interest. Now your quantity of interest is probability density. And so typically what you are able to prove in that context is that at the end of the day, when you pass to the limit, when n is equal to infinity, when n goes to infinity, you get an equation on this quantity of interest, this new quantity of interest, which represents the density of agent with opinion x at time t. So basically it's as if you were counting how many people has this opinion, and you don't care about where it comes from. And so typically in that case, you reach a new equation. So this is a partial differential equation on now your new quantity of interest, which is your density of agents. And as you can see, maybe you can notice in the Excelman-Krauss dynamic case, in the definition of your equation, you have a transport term, so the density of particle we've moved a long time, and you can recognize here on the transport term the function that was used to define the interaction coefficient. So it appears also at this level of description. So what is the limitation of this approach? Well, as I told you, it was first introduced in the context of gas dynamics. And so typically in the context of gas dynamics, you have a property which is called indistinguishability of particles in many cases, meaning that if you exchange the identity of two particles, your dynamic will not see it. It will be exactly the same. You exchange the name of the particle, you make the time evolve, nothing will have changed. So of course, I started by telling you that I'm interested into social dynamics models. So you can guess that in that case, the identity of the people will matter. And so you are not able to work in that framework which require indistinguishability. So as the other approach, which is actually based on some concept object of issued from graph theory. So this is the graph limit. So what is the graph limit? It's I like to introduce it in a particular example which allow you to understand. So I'm not here today with you, but let's say that I'm in the same room as you, and I put all of you on one line, and I'm telling you, okay, so you're all on one line. From now on, you only have the right to interact with the two people to your left and the two people to your right. Okay, so look at them, remember them. This is the only one you have the right to interact with. So you can split again. So now you know the only 4 people you are allowed to interact with. So this is exactly the model which is described here. And I don't know if you noticed, but this is significantly different from the previous one. Why? The Excelman-Krauss dynamic I described, a priori, everyone could interact with everyone as long as your opinion were close enough. That was the idea behind the model. In that new framework that I'm describing, well, you could have almost the same opinion. If you were not seated 2 seats below the person, you will not have the right to interact with it. So basically, we are saying that the interaction are actually based on a graph which describe which interactions are possible or not. So there is a network behind this system which describe the possible interactions. And so this is one way of representing it, as I explained it to you. Another way is through this approach here. So I will not explain in detail how you build this function. The main idea is to understand that when you have a graph theory, you have what is called adjacency matrix, which is matrix where you put 1 or 0, depending if you have an edge or not, an edge between the vertices, okay? So something which connects 2 people. And so when you have your matrix with your 1 or 0, you can actually do a pixel version of this matrix. And this is nothing else than what I was describing. You can only interact with the L people to your right and the L people to your left. And the advantage of this new representation with the pixel is that if you play to put n bigger and bigger, I think that's in that case, and it's equal to 1000, something like that, you can put n bigger and bigger, and you will see to what you will converge. So basically, you will have a limiting object. And this is crucial. Why? Because I started by telling you that my interests are to do the large population limit. So to put n to infinity. So of course, I'm interested into knowing what natural limit object I'm getting when I put n to infinity. And so, for instance, in that case of the nearest neighbor example, you will reach a function which is an indicator function of size theta, like that. And so typically, when I will do my large population limits, I expect to get a limit object coming from my graphs, which will appear in my equation. And so this function here is actually called a graphon for graph function, and it's those natural limit objects that you built exactly as you can see in this picture by putting n bigger and bigger. And so if I want to show you a little more precise results, so now you have a graph. So far, I've discussed what is called simple graph, meaning that you know if you have an edge or not. So if you have a relation with the person or not. But I've started by telling you that not all the relationships have the same impact on you. And so in order to take that into account, you have to work with a weighted graph, meaning that not only you know if you have an edge, but you know the weight associated to the edge. So for instance, here, I have an edge between 1 and 2, and 1 has a weight of W1, 2 on 2, and the same for 2 on 1. And so now you have this system here, which describes the interaction between the people, knowing that they have an interaction coefficient, which is given by this graph. And so the graph limit, it's the fact that when you work with this particular weight here, which is built by averaging this function here, you actually converge to this equation. So I would say on that part, what I would like for you to understand, if not all the subtlety, is the fact that you can start from a microscopic dynamics, and putting n to infinity, you can get a new PDA equation. And you would say, okay, nice, but why? What is the interest of doing that? And that's actually a good question. It's linked to what I've started to describe first. It's the first big class of problem, which are long-time behavior. The thing is to study those microscopic dynamics and to see, for instance, in my social dynamic context, if you get consensus or cluster, you actually have to study the property of connectivity of your graph. And so typically you have to work with your matrix of weights, which is a big matrix. If n is very big, let's say you have a population of 1 million people, you're working with a 1 million and 1 million matrix. So it's a very big matrix. So it has challenges from a computational point of view. And the thing is, you actually extended that framework to say that, well, when n is big, actually, well, a solution to this microscopic system is not so far away from a solution to this system. So I will exchange this one against this new one, which actually is slightly nicer because now the quantity that you will work with is nothing else than a bounded function. Okay, so you exchange very big matrices against bounded function on which you will then do some analysis work. So this is one of the advantage of this approach. And so if I do the link with the first framework that I've described you, so far I've discussed two limits. I've started by telling you the mean field limit in the case of indistinguishable particles that I recall here. And I told you about the graph limit. Well, actually, the thing is you can also study the mean field limit in the non-exchangeable particle system. And how? How do you do that? Because I've started by telling you that, well, in the framework that I show you with my mu t of x, which is the density of agents with opinion x at time t, well, it was not a suitable framework to study non-exchangeable particle system. But actually, if you add a new parameter here, psi, where mu t psi of x, now what does it represent? It represents the density of probability of finding an agent with identity psi, opinion x at time t. Then you added a new parameter, and which is the identity, and you actually in the good framework to now perform your mean field limits. And then you get an equation which is quite similar to the previous one, so a transport equation, but where naturally and hopefully you get this object, this graph found object, which is an object arising from graph theory as a limit of sequence of graphs. So it's normal that you see it appear. So as I was saying, those past few years, there are plenty of people working on that subject because basically because of recent advances in graph theory, we were able to revisit those problems that were not reachable in the case of non-exchangeable particle systems. So plenty of people work on it. So what we did is we did a review paper with my co-author Nathalie, where we go through all this new literature. We presented it in a uniform framework because since it's actually a quite recent subject, well, everyone is working with different notations, and so it's sometimes a bit difficult to understand and relate all the results with one another. So we all presented it in a unified framework, and so we seized the opportunity to actually complete something that was missing on the literature. It was to properly do the link between those different approaches. How do they articulate with each other? The graph limit that I've just shown you before and the mean field limit. So this is what I explained here. So let me recall so far the equation that I've been showing you. Here is the microscopic dynamics. Here is the graph limit equation, and here is the mean field limit. And so how do they articulate with each other? Well, actually, here, those two, this is large population limit. So you obtain them by putting n to infinity. But what is interesting and what we explain in our paper is that actually you can take advantage of the graph limit equation to prove the non-exchange mean field one. So you can either do it directly this way, or you can do it in two steps by first doing the graph limit and then deriving the non-exchangeable mean-field limit from it. So these are for you, I will say, an alternative path to the classical approach. What is interesting is that actually from the non-exchangeable mean-field limit, you cannot always reach the graph limit equation. This is an open question. We know that in very particular interaction functions, so meaning that if phi is very particular, you can go from this one to the graph limit, but in all generality, this is an open question. So here you can see in that picture the general framework of the question I've been interesting. So basically doing those type of arrows and explaining properly the link between those two type of description. And so what I would like to discuss in my talk is three variants of this general setting that I've introduced to you, that I've been doing in the past few years and which can be found in this 4 paper that you can see here. So the three variants are the following. So first, adaptive dynamical network that I'm going to explain right in the next slide. Next slide, random weighted graph, and I will finish by saying a few words about high order interactions. So adaptive dynamical network. I've started by telling you that not all your relationships have the same impact on you. Actually, the other way around goes too, meaning that maybe you've observed that sometimes when you realize that you do no longer share any value or interests with people, you have a tendency to destroy the relationship, so to not interact with them anymore. And on the contrary, sometimes when you find people who share the same value, the same interests, the same opinion on specific subject, you have a tendency to create new relationships with them, and so new edges, new interactions. So once we say that, actually, this is nothing else that to say that the connectivity of your network, of your social networks, it evolves over time. It's not a static things. And as I described, that this evolution actually depends on your states, your current opinions. So the state of the nodes, so the two agents which are involved. And so this is exactly the definition of an adaptive dynamical network. It's the fact that the evolution of the edge ij depends on the state of the nodes I and j. And so if you want to write it in the general form, let's go back to my equation that I've shown you before. So you have the interaction. The novelty is that here the interaction coefficient depends over time too, and that the evolution of this coefficient depends on all the opinions of the population and all the weights of the population. So this is the general form of an adaptive dynamical network. And so what we did in our first paper with Anastasia is that we study a particular one. So what is it? It's the previous model where instead of only being interested into the opinion, now we add a new quantity, mi, which is the agent's weight. So what does it represent? It actually represents, let's say, the charisma, the popularity of an agent. And so you can see in our model that the more charismatic, popular an agent is, the more it has an impact on agent I when it discusses with him, because it will be bigger, so it will make a bigger change of the opinion. And on the contrary, the less charismatic, the less this person has an impact on the other one. So why am I claiming that this is an adaptive dynamical network? Well, because you can represent it as a graph here, and you can see that indeed, the edge weight depends on time, and that the evolution of the edge is coupled with the evolution of the nodes. So it is indeed an adaptive dynamical network, but actually it's a very particular one because, as you can see, all the weights starting from one nodes are the same. So it's a particular one, but still it fits the description of adaptive dynamical network, and this is how we started. And so what we were able to do for that particular framework, we were able to actually extend the graph limit result, which was for static graph, so for graph which do not evolve. So for graph where the weights were fixed, we managed to extend this result to this framework which is more close from reality, where actually your network can evolve with time. And so whatever the details here, I just put this slide to show you that we were able to prove that at the end of the day, we obtained this coupled system of PDEs, which is, in our case of an adaptive dynamical network, the graph limits. So that was actually the first result that we obtained on that framework. The second one I would like to discuss is about weighted random graph. So what is a weighted random graph? So typical example, so a weighted random graph is a graph that you generate by a random process. And the typical example that I love to give, which is very easy to understand, is the Erdos-Renyi graph. So for the Erdos-Renyi graph, how do you build it? So let's say you take a coin. You have a coin and you toss a coin. And let's say that with a certain probability P, you have tail. So you consider an edge, you toss a coin. If you have tail, you draw the edge. If you have head, you do not draw it. And so in that case, it means that you put a black pixel or you do not put a black pixel. And so you do that for all the edges. So you see that this is a random process that you use to build the graph. And those are some examples of realization of Erdos-Renyi graph. So this is the first example of a typical random graph. Another one is the following. Let's say that you start with a sequence of random variables, which all follow a uniform law on 0, 1. So what is a W random graph? You have a function W, and you say, you consider an edge ij, and with probability W xi xij, you build it. And with probability 1 minus W xi xij, you do not build it. Okay, so, and you do that for each of your edges. So for this W random graph, now I'm getting back to my original question, which is still the same, large population limit. What can we say about a microscopic dynamics where the weight will be given by a W random graph? And what does it mean? It will be nothing else than the weights here follows a Bernoulli of parameter W xi xij, because it's 1 with this probability and it's 0 with 1 minus this probability. So this is the Bernoulli of parameter W xi xij. So the question is, can we still, for this microscopic dynamics, which now has some randomness, do the graph limit? And so again, that was a paper of Medvedev who did that. And he was able to prove that indeed, starting from this dynamics, you can reach this partial differential equation that you can see here. So let me comment on that before saying what we did in our case. That is interesting because basically you start with a random particle system, and at the end of the day, you get a completely deterministic partial differential equation. So for those who are familiar with that, this is actually a result in the spirit of the law of large number, okay? And so the question, so when we found this article, we found it right after writing our first paper with that I just shown you before with Nathalie. And our first question was, okay, that is nice to have some randomness, but this is a simple graph here because it's only 1 or 0. Does it still work for weighted random graph? And what are weighted random graph actually? So we did a bit of bibliography and we found a couple of examples. The one that I give here is a Galaskelli model, which is the following. Consider an edge, and again, take a coin, and you toss your coin. And this time, you keep tossing it as long as you have tail. And at your first head, you stop. And you count how many tail you get. And this is the weight that you attribute to your edge. Okay, so this is a process to build a weighted random graph. So now you attribute a weight randomly at each of your edges. And so when we found it, we found a couple of other examples, but we actually find it to be able to address it for the large population limit, something was missing, and that was a general framework. So I say that is one of the first interests of our paper is that we actually provide a general framework on which all the graph in the literature can fit. So we introduced the notion of a Q-weighted random graph. What is a Q-weighted random graph? So typically, for every xi theta, Q xi theta is a probability law. And so you say that you attribute a weight to the edge ij following the law Q xi I xi j. So of course, this is now general and it can fit the framework of Medvedev. You will just have to precise the law here to say that, for instance, in that case, this is the Bernoulli of parameter psi I, W xi xi j. And so the natural question is that, okay, for this much more general framework, can we still perform the graph limit? And so actually that was not so obvious. What do we get at the limit? And so what we were happy to found is that what we get is this partial differential equation, where now what played the role of the graphon is the first moment of the law. So the good news is that it contains the result of Medvedev, because we know that if you have a Bernoulli of parameter W xi theta, this is W xi theta. So we get back at the previous equation, which was previously obtained by Medvedev, but we actually extend this result because our assumptions are less restrictive, and we are able to be more general and to ask less to still obtain these results. And I will finishing by saying a few words about higher order interactions. So far, what I've been discussing is only binary interaction. So meaning that only two people are exchanging at the same time. But the thing is, all of us, we are in a text group, are in email groups, we go to meeting, and we see, maybe you observe that the dynamic when in presence of a group is not exactly the same as if you discuss with the two people separately. Here is a very nice picture that I really fancy, that I've been taking in a paper, which very much describe it properly. You can see that if you are kids, if your two parents came simultaneously yell at you, if you did bad behavior, it will not have the same impact on you, not exactly the same impact on you, as if the two of them came separately to discuss you. So you're missing something in the modeling if you describe only the interaction through binary interaction that you sum, but you're missing the simultaneous action on someone, which can imply a different reaction. And so in order to do that, you actually have to move from the graph theory that I've been describing before. You have two nodes and you have an edge, to the hypergraph theory, where now you can have, for instance, here, those four vertices interacting simultaneously. So for instance, those three are acting on this one, those three are acting on this one, etc., etc. And so now it's not edges, but it's called hyper edges. And so why did we started looking at that? So if I did not convince you with my first explanation, I can show you more. It's actually already used in the literature. So here are a few examples of paper here in the Kuramoto type setting, which is the study of synchronization of oscillators. You're still in the setting of opinion dynamics, where you can see that they go here up to 3 agents acting simultaneously on one, and here 2 acting on one. So it is relevant because it's used in an applied paper. And so the question, the natural one, is that I've shown you in a binary case what are the limit objects built from the graph theory. So now, for instance, if I'm in the case where I can have 3 people acting simultaneously, it becomes that in the case that I've shown you before. And so the limit, the natural limit object, is what we call unbounded rank hypergraphing. So those are the equivalent of the graphing that I've shown you how to build before in the setting of hypergraphs. Okay. And so the question is that now we're interested into microscopic dynamics. So this is a paper that we did with Nastasia Brady and David Poyato. And now you can see that you have L particles which can interact simultaneously on I. And you have here a coefficient, which is here again as before to model the impact of those L on agent I. What is interesting in our model is that we allow for everyone to be able to interact simultaneously, meaning that L can go up to n minus 1. And in that case, the N agent will be interacting simultaneously. And that is interesting because actually from this field, this is very new. There were only one existing result, which is due to Christian Kuhn and co-authors, where they were able to do a large population limit, but in the case of K-uniform hypergraph, meaning that all the hyper edges had exactly the same cardinality and a bonded cardinality. And we wanted to be able to tackle the case where maybe possibly all the agents are interacting simultaneously, so which we can with our framework. And so in that case, what we proved is that, again, we obtain a non-exchangeable limit, so a description of the density of particles, where you can see appearing naturally the hypergraphon that I've introduced before, which is the limit object, natural limit object associated to a sequence of hypergraphs. And so we proved rigorously this derivation in a paper that we released very recently on June this year. And so I guess that's it for my math talk. I will finish by saying a bit about my mathematical journey. So I will start by saying that I'm a bit of a cliché because my two parents are math teachers. So I stay in the family business. But actually, I would say that despite having two math teachers as parents, and having be a very good student my entire scholarity, I've never pictured myself when I was wondering what I will do later as a researcher in mathematics. For me, that was not even possible. I was not able to do that, so I never consider it. And I would like to say that my journey started because I get the chance to encounter a professor who believed in me. And he told me that, of course, I should do a PhD, that I was perfectly, I was very well suited to do a PhD. And this is how my research journey started. And this is when I discovered what it was actually. I think that one of the things that prevent me to picture me as a researcher is that I really didn't know what was the job, the daily job, what you should do. I had this idea that you had to be a genius, and I certainly did not picture myself as a genius. So I never was interested. And he told me that I should do that. And so he actually became one of my advisors. And doing it, I discovered the job and I completely fell in love with the job. And I was convinced that that was exactly what I wanted to do. I wanted to do nothing else. And so I'm still actually amazed to have to be lucky enough to do this job. I'm still not. I still can't believe that I have this luck to do this incredible job. And so this is why, as soon as I could, I decided to be committed to actually try to explain to people what this job is, because I didn't want it to people to be like me and to maybe not consider it by lack of information. And so I started my journey by, since my PhD, going to junior high school as soon as I can to give talks to young people. So I always, when I go there, I always do a scientific talk because I want them to see what is it, what the actual current research look like, what is the interest of the current mathematician. And I also always speak about my journey. I always share my experience, and I explain to them that when I was at their seat, I would never have imagined that I would be doing this job now. And I try to explain them what is this job and why it is reachable if they want to. So I do that as soon as I can. I also, and this is an echo with the first talk that was given this morning, and it was very interesting. I completely agree with everything she said. I really believe in the importance of role models. So I've started to go to high school, junior school and high school, not only to share what my job was to maybe make it seem less impressive and more reachable, but also because I'm perfectly aware that I am a Black woman and there are not so many people. And so I wanted to see that, okay, a mathematician can also look like me. So this is why I was very proud to be part of this exhibition, which has been done by the association. So this is a French association, Femmes et Maths, so Women in Mathematics, which they did 20 panels like this one. And this is an exhibition which goes to different high school, different places. And I have been lucky enough to go with it at many places. And I always love the reaction of the audience, which are very enthusiastic about the different panels. So this is not all researchers. Those are women who did studies in mathematics and computer science, which do plenty of different jobs. Some are in private companies, some are in research, but people are always interested to see real women, actual women doing this type of job and knowing more about their journey and their daily life. And I remember one exhibit in particular where I was near the place, and one Black student came at me and she said, "Oh, I'm so happy to see you. I saw this exhibition, and the first thing I did is like I look if there is a Black woman, and I was so happy when I see you because so far I've never get a Black professor, and so this is tough to project myself because I don't see anyone who looks like me. So I was very happy to see you." And I was very touched because I completely understand what she was saying, because I actually in France, I can tell you that among all the colleagues, I only know one other Black woman as a researcher. So I completely understand why she didn't encounter other people, and I was very happy to be able to be that person for her. I also am very involved into gender equality. So I participated and I organize days which are exclusively dedicated to young women. So they came, they learn about the possible careers. We work on them with them on stereotypes. We make them meet some women scientists, etc. So it's always very nice events. And I'm always it's always a pleasure for me to be part, and I'm very pleased to say that years later we have some message of those girls who say, "Oh, today I'm doing this career, and I have to say that I'm sure that I do that because I participate to that camp, and it enlarged the possibilities of the job that I was able to do." So those are very impactful events that I'm very proud and happy to be part of. And I also do a lot of roundtables when I can, where either I participate or I animate them about the question of diversity and gender equality in mathematics, because, well, the situation is not so good. And so I take every opportunity to discuss it and advocate for better inclusion. And it was mentioned before, I also, because when I was going to high school, I was a bit frustrating because I could only touch a few people at the same time. So I decided to launch on September 2022 a podcast. So I'm sorry, it's in French. So for the French speaking, you can go see it. Where I discuss with some fellow researcher, and where I do exactly what I explained you. We go back, we revisit their journey. They explain the difficulty that they overcome, the obstacles. They explain their job, the math they do, and I'm trying to show a more modern vision of what it is to do research in math. And so the picture that I like to show is the following. I know when I discuss with people that when we are discussing about mathematician, what they see is a white man deceased most of the time because those are former mathematicians. And so I'm trying to show a more diverse, modern, young picture of what it is to be a mathematician. And I think I will stop here, and I thank you for your attention.
That was very good. That was very good. That was brilliant. Sorry, can you hear me?
Yes.
Excellent. Guess what? I have a technical question for you.
Ah, okay.
All right, here we go. Right now, you in your oh yeah, I really like I like all of it, and I like the technical part, and I like your journey. But I have a technical question for you. Now, in one part of your presentation, you was talking about a random network, yes, Australia, and I was just wondering, would the results remain the same if you considered, like, say, a Watt-Stowe-Gotts network, especially one that has, let's say, a small world network? Would that, especially if you're talking about n tending off to infinity, now